everybody. This is Suvarchala, working as an associate professor, Department of Computer Science and Engineering. In this video, I'd like to explain quick sort based on divide and conquer strategy as a part of the design and analysis of algorithms lecture series. So we'll include quick sort, what is the procedure, quick sort, algorithm, and two examples, analysis of quick sort algorithm. So in sorting, already we know certain sorting techniques, insertion sort, bubble sort, and selection sort, and so on and so forth. Insertion sort, designing approach is incremental method, and the data will get sorted by using the memory space, in place memory space, that is the extra memory requirement is not necessary. Best case is order of n, worst case is order of n square. Similarly, bubble sort is also based on incremental method, and the sorting takes place in its place, that is no additional memory is required. But the running time is order of n square. Selection sort, design approach is also incremental, sorting, in place sorting, as well as running time is order of n square. Coming to the quick sort, it's based on divide and conquer strategy, which was discussed in one of the previous videos. And what is execution time? We'll see what is it in this video. And this is also in place sorting, no additional memory is required, much additional memory except for exchange of the elements, that's all. So divide and conquer, just we will revise or recollect what is divide and conquer. Divide the problem into number of subproblems, similar subproblems of the smaller size, which can be executed independently or which can be solved independently. Conquer the subproblems, that is solve problems, the subproblems recursively, and subproblem size is small enough such that the problems is straightforwardly solvable. And combine the solutions of the subproblems, obtain the solution for the original problem actually. So each subproblem is solved independently, no? So these solutions are combined together so that the original problem solution can be obtained. Various problems can be solved by using this divide and conquer, where each smaller problem is of the same type, and the division is going to be made based upon the size of the input data. We have various applications, standard applications, binary search, quick sort, merge sort, Strasson's matrix multiplication, and many more are there actually, which we are going to discuss about these 4 applications of divide and conquer strategy. So I explained you already binary search as a part of the introduction to divide and conquer strategy. In this video, we will go into how quick sort is going to be done by using this divide and conquer strategy. So in quick sort, array of elements are given, or array of keys are known to us, P to R. So that is A of array starting from Q till up to R. And this is going to be sorted such a way that in ascending order or descending order, in general it is ascending order. So part of the divide now, so elements of first part P to Q are going to be lesser than or equal to Q to R actually. Sorting is arranged in ascending order. Divide means here partition the array into 2 sub-arrays. So array of elements are given A1 to N. Those are going to be divided into 2 sub-arrays, P to Q and Q plus 1 to R, such that each element of this first sub-array is smaller than or equal to the each element of the or all elements of the second sub-array. So a sub-array P to R is divided into a sub-array of P to Q and Q plus 1 to R, such that the first subarray elements are lesser than or equal to the second subarray elements. In such a way, we will partition. Conquer means here recursively sort the elements for each subarray again using quicksort. That means if it is able to arrange sorted independently, it's okay. Otherwise, it has to be further divided and so on, so forth. In this specific quicksort, this division is going to be carried out till each subarray contains a single elements. Single element means it's already in sorted order only. So combine. So the next part of the divide and conquer strategy is conquer is over. That is recursively sorting and combine the elements. Combine the elements means trivial. The array is going to be sorted in its place. No, so each element is sorted means automatically the elements are all in its correct position only. So trivially it is sorted. No additional procedure is required in this, specifically in this quick sort, to combine them again because they are in its place. That means each element is in sorted element only. So it's we arrange them in its correct position so that what happens, the elements are already in sorted order. No need to recombine the results in this specific quick sort actually. Now the entire element is sorted by using this conquering concept only. So overall algorithm is going to be, we'll discuss the algorithm in detail further. Overall algorithm is A is an array, P is the lower bound, R is the upper bound. If P is less than R, then we will partition our array into two partitions. So that means where that particular partition takes place at the position Q if you are going to consider. So the first subarray will be from P to Q and second subarray will be Q plus 1 to R actually. That means a particular position we are going to consider as a partitioning position. That element is going to be in its correct position. Such a way we will partition the elements. Because this is a recursive procedure, we would like to analyze the algorithm. A recurrence relation is going to be generated. That is T of n is equal to T of Q plus T of n minus Q. First subarray contains Q elements. Second subarray contains n minus Q elements plus f of n. The function depends upon the partitioning algorithm concept actually. That means how much time is taken to do this partitioning actually. So again T of Q must be used to partition our Q elements. T of n minus Q is again recurring process, that is partitioning n minus Q elements further actually. So how to do these partitioning elements? So a partitioning sub-algorithm is used by us. There are different ways are there to do this partitioning. Each has its own advantages and disadvantages. So array partitioning means we will, in this current example, we will use this array partitioning in which we will select an element as a pivot element around which the partition is going to be done. So one of the elements are going to be considered as a pivot element. We will do the partitioning in such a way that this pivot element is going to be placed in its correct position. Correct position means all elements are going to be lesser than pivot element will be in the first partition of the algorithm. All elements which are greater than this pivot element will be in the second partitioning. That means we will choose partitioning logic in such a way that this pivot element is going to be placed in its correct position. These two subregions, all elements lesser than or equal to this pivot element X is going to be in the first partition elements and all elements greater than will be in the second partitioning element. To do this partitioning, we will use two indexing values ij such that the ith element is going to be passed such. If it is lesser than, it will be replaced as long as it is lesser. When it comes to the greater, then X interchange is going to be considered. We will see how it works properly. So quicksort, these are the correct normal algorithm notation. We have done this algorithm, written algorithm. So algorithm is quicksort. A is an array, lower bound of the array, high upper bound of the array. Initially, we will pass lower bound as 1 upper bound as n, or in other words, depending upon the language, lower bound is equal to 0, upper bound is equal to n minus 1. That is the entire, we are going to see the entire specific range of the elements we will consider. So what is the logic? As long as low is lesser than high, if it is equal means single element is there. If it is greater than means no partitioning is going to be done further. So that's why if minimum 2 elements are there, we have to do, and equal means one element, no need to do further partitioning. One element means no need to have, no, that's why. If low is equal to high means it is equal means single element, and if it is greater than means no partitioning is possible. So what is J here? J is the position of pivot element. It will return that partition logic, partition algorithm, sub-algorithm returns a position J to us where this pivot element is going to be placed, such that all elements of lesser than the pivot element will be in the partition 1 and greater than pivot element will be in the partition 2. So J is the position of the partitioning element, and we are passing the parameters A, array, low, lower bound, high means upper bound plus 1. So after getting this J, we are going to partition in 2 partitions. We got now what are the 2 partitions? Quicksort from low to J minus 1 and quicksort J plus 1 to high. As I told you, J is the position of the pivot element that is not going to be get disturbed. So only we have to further sort low to J minus 1 and J plus 1 to high. Okay. So such a way we are going to consider that partitioning. Again, this is a recursion. Recursion means same again is going to be called itself actually. So that's why we have used recurrence relation also here. T of n is equal to T of q plus T of n minus q. So the base algorithm is the main algorithm is this one only. But what is the logic? So how the partition has to be carried out. The logic is based upon this partitioning carried. So what is partitioning algorithm? This partitioning algorithm, we are passing this A, M, P. M is lower bound and P is the upper bound. And in this partition algorithm considers that A of M is the partitioning element, that is first element. We'll discuss further which element can be considered as a pivot element, but we are considering in this algorithm as always first element of the array is going to be pivot element. So our V is equal to A of M, that is the first element, M is the lower bound of first element, and I is the lower bound as M, J is the upper bound as P. That means these ij values are going to be changing. Instead of changing original values, we are using indices as I is going to be passing or forward direction, J is in reverse direction. I is the index to move our elements from lower bound in the forward direction. J is indexing value starting from the last element, that is moving in the right to left, that is reverse direction. Do while A of I is less than or equal to V, do I is equal to I plus 1. We are moving. I indexing moving as long as our current element is lesser than the pivot element, we are moving. That is, it comes in the first half of the element only, we are moving. When it is not a lesser than value, that is greatest value occurs, there we are stopping. Similarly, we are moving from reverse direction also. Reverse direction means last to first we are moving. How we are moving? We are decrementing. As long as the elements are greater than the pivot element, we are decrementing. When the element comes as a lesser one, we are stopping. That means we are moving forward direction If the elements are lesser than the pivot element, we are moving backward direction as long as the elements are greater than. When these two conditions doesn't satisfy, then the while loops are going to be getting stopped. Then we are going to interchange. If I is less than j, then interchange occurs. Interchange means this greater value is moved there and lesser value is moving here. That means if I is less than j, then interchange. If I is not less than j, no need to interchange. And this entire process is continued as long as I is less than or equal to j. That is, the list get exhausted. The list get exhausted. Up to that we will continue. If the list got exhausted, we will come out of it. If the list got exhausted means our A of m is equal to A of j and A of j is equal to v. That is, we are changing. We are changing and we are returning the j. That is, we are moving our pivot element position to the jth position. By that time, all elements before j are lesser than the pivot element. All elements greater than the pivot elements are above the jth position. So that's why we are A of m is the first element is the jth element and jth element is the first element. That is pivot element. We are interchanging them. We placed our jth position, our pivot element. That j is going to be returned to us. I'll explain you how it works properly. Interchange means just swapping. We need not write separate method for this or a separate subalgorithm for this. It's certain languages like Python. Python directly you can interchange itself. You can interchange itself, right? So how can you interchange? A of I, A of j is equal to A of j comma A of I. Multiple assignment statements are possible in Python. Directly you can write. But we are using algorithm notation. No, that's why we are using separate. Now, we are, for interchanging, additional memory is used for interchanging, swapping only. For example, if you are considering here integer numbers to be sorted as a 20, 40, 20, 10, 80, 60, 57, 30 and 100. There are number of ways to pick the pivot element. In this example, we use the first element algorithm also based upon that only. But I'll discuss at the end of this video what is the role of pivot element and how to choose the pivot element also. So we are partitioning. Given a pivot, partition the elements of the subarray such that the resulting array consists of one subarray, contains the elements of greater than or equal to pivot. Another subarray contains all elements lesser than or equal to pivot, less than elements actually. So the subarrays are stored in the original array itself, no additional memory used. So that's why partitioning of the loops through swapping the elements below or above the pivot element is considered by us. So let us assume that 40 and we are using the elements as a 20, 10, 80, 60, 50, 30 and please find out or check. Yellow color indicates that movement of the ith index from left to right and jth index from right to left. J initially is having our position is 1, 2, 3, 0 starting 0. 8 is the jth position and I is the 1 position. 0 is the pivot element indexing. Blue color. First, it will enter into the loop. I is less than j. Yes. Our lower bound value is lesser than higher bound value. It will happen properly. So I is getting incremented. So please observe that the incrementation is carried out. I plus 1. That means 3 will be considered. Next 4 will be considered. Next 5 will be considered because 40 is pivot element is lesser than, 20 is less than pivot element, 10 is less than pivot element. When it comes to the 80, then it will stop. So when we are considering this pivot element consideration here, the specific values are going to be used here to move the elements to the respective positions. Right? So we are considering here the values as I is going to be moved as a j, and when it comes to the 80 value, it will stop. You observe here. We stop at this incrementation of I. Now ith position is 3. Similarly, moving to the j, j values are checked as long as the greater than value, j is decremented, 100 is greater than 40, decremented. Now j shows to us 30, decremented, then interchange, swapping. 80 and 30 are going to be interchanged. Then what happens? Our I value is passing to swapping here. 30 is going to be ith position as j, jth position as 7 actually. So when it is interchanging, then we start again processing. 30 is less than S, A of I is less than pivot value, continue. And when it is moving to the 60, A of I is greater than pivot value, it will stop. So when it moves 60, it will stop. Coming back to the jth also, j is greater than, 80 is greater than, it will continue. And j is 80 is lesser than, it will stop. Then again interchange considered. 60 and 7 are interchanged. When these two are interchanged, then what happens? Our position is 6, and it is going to be, swapping is going to be carried out and move to the first one. So once the swapping is carried out, what happens? 7 and here previously 7 and 60 are interchanged and started. What happens to now? I is considered to be as a 6, 50 is greater than, it will stop here, and 60 is considered to be as a greater than 40. Then again 50 is considered to be as greater than 40, it will continue. But here I is not less than j, right? So our I is greater than j, the entire process is going to be stopped here. So then it will stop the process. And what is our position of j? J is going to be moved or indexed. A of j and pivot index is going to be moved actually. So what is my jth position? Jth position is indexing 4, and the pivot element and the respective jth position are going to be interchanged. You observe here. 7 comes to the first position and 40 moves to the fourth position. What are the values now we are having? You observe here. Pivot position is going to be 40, and all elements are before pivot element are less than 40. You observe all elements after pivot element are going to be greater than 40. So that jth value is going to be returned. The jth value is 4 is going to be returned. Partitioning has been made in such a way that now you observe all elements before this pivot element are going to be lesser, and all elements above the pivot element are greater than 4. What happens here? If you observe, we fixed this pivot element is in its correct position. So the correct element 40 should not get disturbed. So that's why we partitioned our entire array into 2 partitions, leaving our pivot element in its correct position. So 0, 1, 2, 3 are the first partition. 5, 6, 7, 8 are the second partition. That is 7, 20, 10, 30 are in the first partition. 50, 60, 80, 100 are in second partition. So the pivot element is not now fixed in its correct position. No need to change its one actually. Again apply the same process for the first partition of element, second partition of element. This is going to be recursively continued. So we'll take another example. 5, 3, 2, 6, 5, 4, 1, 3, 7. Take constant pivot element. So when we are considering pivot element as a 5 is going to be placed in its correct position. X is equal to 5. X is equal to 5 means all elements which are lesser than up to 5, that means up to 2, this is going to be continued. When it comes to the 6, the process is stopped. J is coming back again. So while coming back J, as long as it is greater, it will continue. When it comes to the lesser, 3 is lesser than 5, we are getting back. So which are the interchanges are applied? You observe here. So I is moved, J is up to 5 only, and I is moved to the 5, 3 to 6. Up to 6 it will be moved. 6 is greater than it stopped. So then interchange occurs. So it has to be interchange. When it is interchange happens, 3, 4, 1, all are lesser and J remains as it is. So we are going to consider that Jth value only to be interchanged, that is 3. 3, 5 are interchanged. We placed here 3 and 3. 5 is the position, correct position, and all elements below the 5 has to be considered. All elements above the 5 has to be considered. So considering this 5 as in its correct position, we can stop the process actually. So here the 5 was placed in its correct position. Then we are going to pivot element is going to be placed in such a way that all elements are lesser than 5 means 3, 3, 2, 4 are in the first list, and 6, 5, 7 are in the second sublist. 5 is pivot element, no, we can stop. Such a way you can continue. You observe the recursively. So first pivot 3, if you are considering, 1, 2 will be in the first list and 3, 3, 4 will be in the second sublist. 1 means the pivot element, 1 will be in the one list and 2 will be in the list, then it will be stopped. 1 in its position, 2 is in its position. Coming to the 3, 3, 4 also, 3 is in one list, 3, 4 is another one list, and 3, 4 is further subdivided, 3, 4. Now you observe what happens. The list 1, 2 and 3, 3, 4. That means we are placing a pivot element in its correct position means those are already in sorted places actually. Coming to the second part here, when we are considering the second part, 5 is pivot element I have taken. Then 5 is in the first list, 6, 7 will be in second list. 6 is in one list, 7 is. Now you observe 5, 6, 7. Now automatically those are in the place itself. So that's why in the beginning of the video we consider quick sort, no need to combine the result, because the conquer itself is taking place in such a way that the pivot element is placed in its correct position. So no need to again recombine the results at all. So when we are considering this recurrence part as T of n is equal to T of q plus T of n minus q plus n, where n is the time taken to partition. You observe what is the algorithm we have used for partition. Partition algorithm consists of for while loop, and this while loop is going to be as n times it get executed. So we can consider it as a n only can be considered actually. So the function f of n we have written in the initial stages, that f of n is nothing but, in this example, partitioning algorithm, time complexity can be considered as a n. Such a way we can partition algorithm. So divide and conquer algorithm based quicksort takes lesser time comparing with our other incremental algorithms discussed earlier actually. The recurrence is based upon the 3 steps. So any recurrence algorithm, if you are using a divide and conquer technique, if you are going to consider while analyzing the algorithm, we can use recurrence relation. So the recurrence relation is going to be used based upon the recursive process you are going to consider here. So the recurrence is based upon the 3 steps. T of n is running time of a problem size n, and divide the partition problem into a subproblems, each of size n by b. Okay, so that means it takes B is any constant of equal sizes. Conquer, solve the subproblems as A T of n by B. A subproblems are there, no, that's why. Combine the solutions with constant time takes C of n. So T of n is equal to theta of n if n is less than or equal to C, and A of T of n by B plus D of n plus C of n, otherwise where C of n is the constant you can consider. Based upon this recurrence paradigm, we can analyze our algorithms, quicksort algorithm for various cases. Worst case, average case and best case also. First we will discuss worst case. Worst case means depending upon the worst case occurs when the partitioning is going to be done is a worst case partitioning. What is worst case partitioning? One region has n minus n elements, another region has only one element, then you can say the partitioning is going to be worst case. That means you observe here n elements are there, first partitioning 1, second partitioning n minus 1. Again n minus 1 elements are divided into two partitions, 1 and n minus 2, and so on and so forth. So the time taken to this process is n minus 1, n minus 2, etc. up to 1. So totally n into n minus 1 times, so order of n square will be the algorithm complexity. Coming to the recurrence part, T of n is equal to T of 1 plus T of n minus 1 plus n. N is the partitioning algorithm complexity. So T of 1 is equal to 1. Then the total number of partitioning or total complexity will become as a theta of 1 plus theta of n square, which is theta of n square only. So when this worst case happens, that means that every time the partitioning takes 1 and n minus 1 sizes. When it happens generally, there are many arrangements may be there which may result worst case actually. But we will consider common two cases. What are the two cases? When our list is already sorted order. So when the array is already sorted order, worst case occurs. Already sorted order means when I would like to take the first element what happens? Already in its position, no? So the dividing or a partitioning algorithm takes two sublist which contains first sublist as a 1, second sublist as n minus 1. So when the list is already in sorted order, worst case occurs. Because always partitioning into two partitions creates or generates one element in one partition or remaining elements in the other partition. Similarly, another situation when the array is inversely sorted. Array elements are opposite sorted also, it happens like that only. N minus 1 elements in the first sublist, 1 element in the second sublist, and so on and so forth. So that means worst case partitioning always divides the array into these three parts. A length of one part containing the pivot element itself, a length of 0 part, and the length of n minus 1 as other part. We don't recur the 0th length part. Always recurring is going to be done on the n minus 1 part only. So that's why in the worst case recursion may be n levels deeper. So n levels deeper, so that's why n times it occurs. And number of times n is going to be repeatedly done, no? So that's why partitioning works on order of n star order of n, totally order of n square. So the worst case of quicksort is going to be order of n square. Now you observe, this is our list. 1 in the first sublist, n minus 1. Similarly, n minus 1 again further partitioned, 1, n minus 1, and so on and so forth. So worst case time complexity is order of n square. Best case. This best case partitioning means partitioning produces when two regions are of the same size almost, n by 2. Then we can say it is occurs as a best case. That means the recurrence is going to be considered Q is equal to n by 2. That is T of n is equal to recurrence relation becomes as 2 into T of n by 2 plus theta of n for partitioning. Anyway, T of n by n is equal to n by 2 times it is doing. That means our tree depth is going to be n by 2, that is log n. Every time we are dividing, no, so the height of the tree will be n size. So log n will be our depth of the tree. So totally n log n will be our partitioning. So that's why when n times it is partitioning is going to be done. So that's why log n is the height of the tree. N log n is our plus order of theta of n will be there, which is having a lesser priority. So the highest term is going to be n log n. We can prove this by using our master's theorem or any substitution method also. So you observe this is the height and the n times partitioning is making. So n log n is our the best case partitioning. So when it will occur whenever the partitioning is going to be almost done of equal parts, that is n by 2 parts, then best case occurrence of the possibility of best case is considerable. So this is the best case. We cut the array size into half each time. So the depth of the recursion will become order of log n to the base 2. That is the height of the tree. At each level of the recursion, all the partitions are at the level will work in a linear time n. So that's why order of log n to the base 2 multiplied by order of n, which is equal to order of n log n to the base 2. So the quicksort best case is going to be the complexity of order of n log n to the base 2. So you observe, this is the diagram. Every time it is divided into exactly almost equal partitions, then the best case possibility will be considered. In between these two, worst case and best case, that is average case. Worst case and best case between, average case is going to be 9 to 1 partitioning proportional split is going to be done. 9 to 1 means 9 parts in one place and 10 parts will be in the other place. Now you observe here Q of n is equal to Q of 9n by 10 and Q of n by 10. Division is going to be carried out. So this is going to be order of n. The size of the height of the tree is going to order of n. You observe in this case also n every time the partitioning takes. So using this recursion tree, the longest path is going to be n log n and shortest path is also n log n. So that's why our quicksort average case algorithm is also order of n log n. So if you observe here 1 by 10, 9 by 10. 1 by 100, again 9 by 100. That means 9 by 100, 81 by 900, n minus 1. So like that, if your depth is going to be observed, it can be continued till height of the tree is going to be log n to the base 2. So any splitting of constant proportionality yields theta of n log n time means here. Consider the 1 to n minus 1 splitting. The ratio is 1 by n minus 1, which is not a constant. But n by 2 to n by 2 means it is a splitting is going to be ratio is going to be n by 2 by n by 2, which is equal to 1, which is a constant. 9n by 2, 10 and n by 10 is also equal to 9, which is a constant. So if you observe that a partitioning, depending upon the way the partitioning is going to be done, depending upon which the performance of the quicksort is going to be considered. So any a minus 1 by a minus 1 into n by a to n by a splitting is going to be done, then it is almost equivalent to the constant only. So that's why if it is splitting is going to be done such a way that the constant number of elements is going to be carried in first partitioning as well as second partitioning, which may be keeping on improvising, then the respective time complexity is going to be order of n log n. So that's why if the partitioning is having some ratio of splitting such that the ratio becomes as constant, if the ratio is constant, then the complexity will be n log n. If the ratio is not a constant, the complexity is more than that actually. So the performance of a quicksort, average case, worst case, best case we have seen. So worst case is going to be order of n square, best case is n log n, even average case is also n log n only. That is, all permutations of input numbers are equally likely happens, and random input array we will mix well balanced and unbalanced splits. So good and bad splits are randomly distributed across throughout the tree, then average case performance is going to be considerable. N is divided into 1 to n minus 1. Again, n minus 1 is further divided into half. That is combination of best and worst cases. Combine the partitioning cost. Then it will result n by n log n only. So partitioning cost is going to be n minus 1 are divided by further. And sometimes it may be nearly balanced, nearly unbalanced. Both combinations are there. Average case performance occurrence is possible. So the running time of quicksort when levels are alternate between good and bad splits, then also we will get the complexity as order of log n to the base 2. So if the array is already sorted to the begin, quicksort is terrible, that is order of n square. If the possible to construct and other bad cases, quicksort is usually order of n log n. The constants are so good that quicksort is generally considered as a faster algorithms. Most of the real-time applications are based upon our quicksort only. But one problem is here to be considered. That means a special case has to be considered to get the good analysis of the quicksort actually. How to choose a pivot element? How to choose a better pivot element so that the analysis is going to be very effective mannerly identifiable by us. That is, we pick the first element of the subarray as a pivot element in the examples which we discussed. But it need not be always the first element. It can be any element can be considered as a pivot element. If the array is already sorted, this results order of n square behavior. So if no better, even if you pick the last element also. So if the pivot element is going to be chosen as a middle element, if it is already sorted array, then our quicksort takes only order of n log n only. That means if median is going to be taken, middle element no, pivot element, then it partitions into sub to sublist and so on and so forth. In such case, the complexity becomes as a order of n log n. I mean to say that if the elements are already in sorted order, if the choosing of the pivot element is going to be a median, then it will result as a best case only. We could do the optimal quicksort, guaranteed n log n, if we always pick a pivot element value that exactly cuts the array into half. That is, choosing of a pivot elements affects our analysis of our quicksort algorithm. So that's why pivot element value is called a median. If you take in such cases, half of the values are in the array are lesser than no. So that's why in the first half, greater elements are in the second half. That is the easiest way to find the median is to sort the array and pick the value in the middle element. Again, sorting means again it will take more time. So that's why it does not make a sense to sort the array in order to find the median to use a pivot element. Instead of that, compute just 3 elements of our subarray, that is first, last and middle, and take the median of these 3 elements. Then possible but not easy to construct the cases which will make this technique as a order of n square can be get reduced. So that's why pivot element, to choose the pivot element is sorting is not a optimistic way of choosing pivot element. So that's why generally we'll take 3 elements, first, last and middle element. median of these three elements can be considered as a pivot element. Sometimes it may result as a effective process of or effective analysis of the quicksort actually. So that's why choosing of a pivot element also affects our analyzation of the quicksort. So it has to be decided first element, last element, or median, or sometimes random element. It all depends upon that. So the analysis affects the pivot element selection also. So the selection of pivot element also plays a vital role in analyzing our quicksort algorithm. And also size of the array. For very smaller sizes, quicksort doesn't perform well as uh, well as the insertion sort. For example, cutoff range n is equal to 20, then it is the time taken quicksort is almost the same as our insertion sort. So switching to insertion sort for smaller arrays can save almost 15% of time, execution time. So better use smaller values, insertion sort or some other sorting technique instead of using a quicksort. This affects or gives optimistic results if the size of the array is very, very going on increasing, larger sizes only. For smaller sizes, it doesn't give much effectiveness actually. So that's why quicksort must be used for larger sizes of values, key values. That is, n size is more greater, it is going on increasing. Quicksort is most effective one, as well as choosing of the quicksort plays a vital role while analyzing our quicksort algorithm. So we have to keep in our mind these two cases, special cases, and apply quicksort if necessary to get the best complexity or time taken to sort the data is very, very effective one actually. Okay. Thank you for watching this video.
Like, share and subscribe. Hit the bell icon for more updates.